Okay, so in the first half of the lecture, we derived the weak form of our second order differential equation, and we discretized it by just choosing a discrete subspace, and we proved that we got a solution, which is good news. What we're going to spend probably much of the rest of this lecture on is working out whether or not it's in any sense a good solution, because it's not sufficient to produce any old solution. We'd like one that has some sensible properties, and that therefore might one day be useful to someone who actually cares about the science as opposed to about the maths. And the first interesting thing we can notice is we've now got actually two different versions of the weak problem. So out there, we've got A of u v equals fv for all v in v. So that was the continuous version of the problem, where we defined a function space out there. And we've got A of us v prime, if we want to make a difference here, is equal to f v prime for all v prime in S. And so this guy out here, if we permit him to be sufficiently smooth, if this guy is sufficiently smooth, is a solution to the original problem. And if we don't permit things to be sufficiently smooth, it's the solution to the weak problem in the biggest available function space for solutions to sit in. Whereas this guy is our discrete solution, and he lives in a much, much, much more restricted set of function spaces. So it's possible that this guy is equal to this guy, but quite likely that it isn't. Right? Because it's quite likely that this solution out there is not in our discrete space. So if you think about the continuous version of the equations, this is probably a nice smooth function. And if you think about your finite element approximation, well, in the simplest case, it's a piecewise linear approximation. The solution is probably therefore inexact, and there's some sort of error. Well, the first thing we can note is, remember that S is a subset of V. So what's the one trick in finite element? We choose our test function. So in particular, we could choose V in S. Right? If it's true for all V in V, it's definitely true for all V in S, because S is smaller than V. And so now if we do that, we can subtract these two equations. So we can say for any given test function, we have A of u minus us v equals 0. They're the same for all w in S. So what did we just write here? So this is the error. Right? This is the difference between our discrete solution and the continuous solution to the weak problem. And this is any function at all. Sorry, that should be a v there. I'm getting confused between my notation and their notation. This is any function at all in this space. So what does it mean for this to be 0? Well, that looks like an orthogonality relationship, right? If we consider A to be an inner product, then this is saying that in this inner product, this error term is orthogonal to, invisible to, if you like, all functions B. Now, is that a fair characterization? Well, let's just jump back a little bit and ask ourselves a question about A. is it the case that A is in fact an inner product? Well, A is definitely bilinear in its arguments. It's commutative. If I swap the two arguments of A, I get the same thing. And for a sufficiently well-behaved class of functions, as we just argued earlier, A, V, V equals 0 is equivalent to V equals 0, right? So if we restrict ourselves to functions whose derivatives are in some sense well-behaved, what this is saying is that when I integrate the square of the derivative, then the function is 0. So that's the argument we use for uniqueness. So that property of an inner product is satisfied. And remember what AVV is equal to? That's equal to V prime squared dx. So because that's a squared, this thing is definitely positive. No way for real valued functions, and we're only interested in real valued functions, that I could possibly get a negative value out of that. So yeah, actually, A behaves exactly like an inner product. It is an inner product. And so this is the fundamental orthogonality relationship that says what's going on in the finite element method. Right? What it says is, for this particular problem, for the error is orthogonal in this norm. This norm is known as the energy norm, for reasons we don't need to go into. Is orthogonal to this whole function space. So what that sort of means is that, like in an intuitive sense, what's going on is we've solved the problem in this space. So looking just in this space, there is no error. The error occurs in the things that this space can't see, in the difference between this space and the continuous space. That's where the error in this system is. That's what the orthogonality relationship is saying. So that's kind of nice because it leads us to an intuition that we suspect that if our discrete approximation to our continuous space is somehow good enough, then maybe that error is not so important. And that's the sort of direction of travel we're going in the proof. We're trying to demonstrate that if we've got a sufficiently good approximation to the continuous functions, then we have a sufficiently good approximation to the continuous solution. And that's good because then we know how to build discrete function spaces that look a lot like a continuous one. So then life is great. So as we learnt last week, anytime I have an inner product, I have a norm. And so we can define an energy norm, so called E, energy, and that's just equal to the square root of A, V, V. So that's, just as we learned last week, the norm induced by this inner product. So nothing new there. And one of the important things that we learnt is that the inner products obey this Cauchy-Schwarz inequality. Right? So the Cauchy-Schwarz inequality says that if I have the inner product of two vectors, by which in this case we mean functions, then that is less than or equal to the norm of the first one times the norm of the second one, where the norm here is the norm induced by this inner product. So that's what we learned last time. And now we're going to use it to say something about the errors that we've got. So we've already noticed that the error in our solution is u minus us. And so if we want to say something about how big the error in our solution is, then we can take the norm of that error. So what we can say is that And what we need to do is manipulate this back in the inner products. And remember that the norm is the square root of the inner products. So what I'm going to do is I'm going to square this. That's still useful, right? If I've got a norm, I can square the norm, and it's still an indicator of size in some sense. And that is then equal to and now trick number one for the finite element method. Let's get a test function in there, and then we can choose which test function we're going to use, right? And so what I can do is use the linearity of this norm, linearity of this operator, this inner product, to put in here any function I like from the appropriate space. So u minus us, u minus v, plus a of u minus us, v minus us. So I've done nothing there, right? Because if I add those two back together, those two v's cancel and I get u minus us back again. So just because this is linear in that argument, that's a nothing operation. However, I have actually done something useful, because if I choose v out of s, then remember this thing's not in s, this thing's in s. This thing's not in s, this thing's in s. Not in s, s. So none of these expressions themselves are in s. But this is in s, and this is in s. So this right-hand side here is a function out of my space s. Right? I've chosen v to be in s, and u is a solution s. So that thing is in s. And what did we just prove? We just proved that the error in this norm is orthogonal to everything in s. So because both of those things are in s, that goes away. It's using the thing we just proved. It's using the orthogonality relationship, right? So what we did effectively was we split the right-hand side into a bit that was in s and a bit that wasn't necessarily in s, and the bit that's in s goes away. So this is interesting, and now what I'm going to do is I'm going to use my Cauchy-Schwarz inequality. And so what I'm going to do is I'm going to say that that thing is less than or equal to u minus us in the error norm, energy norm, sorry, u minus v in the energy norm. So now there are two cases which are interesting. One of them is that u is equal to us. Well, if u is equal to us, then the error was 0, so I'm happy. Right? I'm always really, really happy if I can solve a system and the error turns out to be 0. So the only case we actually care about quantifying the error in is in the case where the error is not 0, and in the case where this is not, the error is not 0, I can divide by this, right? That's just a number, that term. So we divide by that makes that go away. So now what we see is that the norm of the error is less than the norm of the difference between u and v for any v in my discrete space. So in particular, if it's true for any v in that space, it's true if I take an infimum. So this is less than the smallest such error. So the infimum, so infimum is a technical mathematical term in these spaces. You can think of that as just meaning minimum. The difference between an infimum and a minimum is that a minimum must exist in the space you're looking at, and an infimum need not be in the space. It might lie outside the space. Yesterday I mentioned the concept of Hilbert spaces, which are complete spaces, and said don't worry about it. Well, because we are in Hilbert spaces here, because all the spaces we are looking at are complete, the infimum is the same as the minimum, because all convergence sequences converge to something in your space. So for these purposes, infimum and minimum are the same thing. And so that is equal to or less than the infimum of u minus v e for all v in S. And actually, US is a v in S, right? US is a function in that space. And so what that tells us, if it's less than or equal to the minimum for all v's in that space, and it is one of these things itself, well, it can't be less than all of them because it is one of them. So it is equal to. And because we achieve our minimum, I don't need to write infimum anymore, I can write minimum. So what has that said? What that said is that the solution we got by solving that discrete system is, when measured in this norm, the best possible solution. It's the solution where the error is minimal amongst the total class of solutions that we looked at. So that's quite good. That tells us that given the way we chose to approximate our function, we have the best possible function. So I think the last thing we're going to do in this rather heavy and theoretical lecture is we're going to try and say something sensible about that number, because the interesting thing there is I've proven a whole lot of stuff in a norm that you're not really very familiar with, right? This is some weird new concept of size, which doesn't look like the concepts of size that you're used to. It doesn't look like a Euclidean distance or anything like that. And so what you would hopefully like me to be able to show you now is that, having proven that this solution is in some sense a good idea in this measure, it's also a good idea in a measure that you understand, like integrating the functions and checking that they're similar to each other. Right? That would be a much nicer and much more familiar place to be in. And so let's so what we want to do is we want to use what we know about this error in the energy norm and attempt to say something about what's going on in the in the normal L2 norm, the norm that we sort of think we understand. So let's go back. And so we're going to define a number that we might need a bit later, so a function. So minus w prime we will define to be u minus us on so what I'm doing, so I'm going back to V, so W is in my big continuous space, and I'm using W to solve the original differential equation. I've just made a particular choice about what my right-hand side is going to be. Right, so I'm same boundary conditions, different f. But that's an f that's in an appropriate space, right? It's a perfectly valid form of this differential equation. If you believe that the original differential equation has a unique solution, you have to believe this one does as well, because it is the same equation. I've just made a choice about what's on the right-hand side. I'm going to come back and use that. So what we do is we say, right, let's look at how big the L2 norm is. So to satisfy the pedants from last week, I'm not writing L2 down there because it's in some sense the natural norm on these function spaces. And so that is equal to the L2 inner product of U minus US, U minus US. And that is equal to the inner product of U minus US minus W prime, just by definition, right? I wrote down that definition. That is equal to okay, so that just comes back from my definition of A. So I defined A to be the operator for this differential equation in weak form. And because U and US have to satisfy the boundary conditions, as we demonstrated earlier, when I integrate this by parts, the boundary terms have to fall off, because this is U and US in particular, so it's not just any random function on the right. So that's why I get back to my favorite operator. And that's also true what's going on here? Oh, yes. If I subtract off V for any V and S. Right? The reason for that is that A of U minus US inner product with V is 0. That's our orthogonality relationship again, right? So if the inner product of that is 0 and the inner product is linear, I can always subtract that off the right-hand side. I've just done nothing to my operation.
So the previous step,
yeah.
You've got FV, where V is minus W prime, double prime.
Oh,
and
sorry. Yeah. Yeah, no, that's right. Yeah.
Yeah. And then
this is an A, right?
Yeah, but A is
the integral
A is
of
A.
I need to use different letters here to avoid confusing things. G prime, B prime. So I get from this one to this one by integrating by parts. And the reason you should be worried about having just A here is because there should be boundary conditions. But
okay, so
there aren't boundary conditions because I defined W up here to satisfy the boundary conditions. So that works.
So you can integrate by parts twice?
No, just once.
How do you use both the derivatives on W? Oh, no,
because there's one derivative on each thing inside A. Yeah. So it's just integrating by parts, and because I said that W satisfied the boundary conditions, the boundary terms drop off. So I get back into my weak form equation, right? And then I added nothing to it. And obviously the reason I added nothing to it was so that I've now got a term which is a difference between something in my big space and something in my discrete space. That was the motivation for that trick. So now we're going to use the result of the day, which is the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality enables me to split this thing up, and so that is, not equal to, but less than or equal to the U minus US, the error norm, W minus V, the error norm, and I keep calling the error norm, that's just rubbish, it's the energy norm. And so now, what I want to do, so this is a statement about the square of this thing. So once again, assuming that the error is not 0, because if the error was 0, then life would be great and we wouldn't care about this operation. So assuming the error is interesting, then what I can do is I can say this is actually u minus us, and put the square there, but then take it off, and divide this thing by u minus us. And now notice that this is not in the energy norm. And not only is that not in the energy norm, I can use my trick again and say, well, I know what that is. That's W double prime by definition. And so now what's going on, short my tongue here, is I've got a statement about this norm in terms of this norm and W and V. So now we need to attempt to say something interesting about W and V. So what we would like to be able to say is, so let's just rewrite this slightly in a more intelligible form. What I'd like to be able to say is that this thing is small. Because if that were true, then what I'd be saying is that the norm of the error in the norm we understand is small compared to the one where we've already proven it's good. So that would be really nice territory. That's where we want to get to. Well, one of the things we can already do is we can already point out that this is true for all V and S. So it's true for the infimum of this. So it's true for the best possible V. So that's a very good start. And now what we would like to do is we would like to say something about the relationship between these two. In fact, what we would like to say, and this is kind of probably about the last thing we'll do today, is we'll write down the statements we'd like to be true about this, and we'll argue as to why that's a fair thing to do. We'd like to be able to say the case, if I take W in V, just some W, I'd like to be able to say that the infimum of V in S, so that's to say the best approximation by something in my discrete space to this function. We'd like to be able to say that the energy norm of that is less than or equal to some hopefully small parameter times this. So that's just rewriting the previous statement. This is what we aspire to have being true. And what we are effectively saying there, it doesn't look like such a big leap. Oh, I used the wrong norm. I have used the wrong norm. Sorry. This is an energy norm. So remember now, this thing is So in some sense, that and that are both second derivatives, right? This is a sort of weak second derivative because it's this thing, and this is then the straight pointwise second derivative. And so what we're kind of trying to say is that if we are good at approximating second derivatives, then everything falls out and we're done. So we're saying that if we have a sufficiently good approximating space in just the properties of the approximation, then we have shown that the properties of the solution fall out. So that's really good news. And this is why, those of you who had some exposure to finite element, we spend all our time worrying about getting the finite element spaces to have the right properties. Because once you've got the right approximation properties in the spaces, this result proves that you must have sufficiently good results in the in the solutions. So we are just about out of time now, which is convenient because we've got up to a particular point. So what we're going to progress on to next time is we're going to, at the moment, what we've done is we've gone from writing down a differential equation to sort of abstractly showing that if we had a suitable finite function space, we could solve it, and we would get a solution which is in some way good. And so what we need to do to go on to next time is to actually having a suitable finite dimensional subspace, and it will turn out to be P1, right? P1 is a perfectly good space for this one, and we'll show that P1 is a space for which these properties hold, and therefore that we get a good solution. And we'll move on after that to covering some of the things about what that practically means for how the implementation works. So I guess we should probably wind up there. Are there any questions at this point? Stunned silence. You've all been beaten into submission. Good. Okay, so we can probably kill the recording now. And